Okay, guys, this is Mr. Krieger. It's Algebra 1. We're going to do Lesson 6. We're doing the first few pages of Lesson 6 here in the video. We'll do the rest of the lesson in class, live on the Google Meet. Okay, so here it says decide if each of the following relations are functions, then find the domain and the range in the interval. So let me go over first what it is to be a function. We had said today in class that a function is when the x values don't repeat. So take a look at these values. So let's say 1, 5 and 2, 7 and 3, 12. So these are x values and these are y values, x and y, x and y. And being that the x values in each case, they're all different, 1, 2, and 3, this relationship between all these is going to be a function because the x values didn't repeat themselves. The domain of this function is going to be all the x values. So we would say the domain is, usually we put this x so we know x represents domain. And you would put all the values, 1, 2, and 3 for the domain. And the range values are simply all of the y values. So 5, 7, and 12. Okay, so that's what you need to know about functions. The x's don't repeat. The domain are all the x values, and you don't have to, if there's multiple values that are the same, you only have to put one instance of each. And all the y values together make the range. And let me show you what I mean by that. I'm going to make another relationship. Let's say 3, -2. Let's say 5, 8. And let's try 7, -2. Okay, so is it a function? Well, the x values are all different, so yes, it's a function. And then the domain is going to be all the x's. So put them in order, 3, 5, and 7. They're already in order. And the range are going to be all the y values. But notice the -2 repeats itself twice. We only have to do that. We only have to show one instance of that, -2, and then there's an 8. So just write down all of the y values, but you don't have to write -2 twice. You're only going to write that once. You don't need to put repeats. You shouldn't put repeats, just each value once. So -2 and 8, that's the range, okay? Now, these functions or relations, you'll notice there's only three items in each. 1, 2, 3. This pair, and this pair. But you could have lots of pairs. You could have 10 pairs, 20 pairs, 1,000,000 pairs. And you could also have a situation where you have an infinite number of pairs. See, a function like this or a relation like this, the values go on forever. They don't stop at the end of the graph. There are arrows on this thing that's going on forever. But not only do the relations go on forever to like x getting really big, like 20 and 30 and 50, but even values in between, like even decimal values, like 3.5 or -2.7, those values are all accounted for. Now, the way we know which values are accounted for is we could go to a specific x value and see if the graph is there. So like at -2, it's a little hard to see, it's just a little small, but at -2 here, if you go down to the graph, yeah, the graph is there. If you go over to positive, let's see, that's 2, 4, 6, +8, yeah, the graph's there. And in fact, no matter where you would go, the graph would be there. So essentially, every single value for x is involved here, and the associated y value. So when you find an x value, let's say x is 6, then there's the associated y value here. It actually turns out that when x is 6, y is also 6. When x is 4, y is actually 2. When x is 2, y is actually 0. But every x and y are related to each other. There's a pair for them. The dot on the graph will tell you that pair, 5, that would be, let's see, 1, 2, 5, 3 is a pair. Okay, so just be aware that you can still get pairs like these pairs, except there are so many pairs, you couldn't possibly just write them out like this. There are just too many to write out, so we wouldn't do that. Now, this is a graph, and it shows the relationship between x's and y's x on this axis and y on this axis. And how do we tell if it's a function? Now, I told you before, when you have pairs like this, you would just look at all the x values and make sure they don't repeat each other. Then it's a function. How could we tell when we have a graph like this? Well, we have a shortcut, a quick way to tell. It's called the vertical line test. And the way it works is simple. You just imagine, you don't have to draw them out, but you just imagine that if you put a vertical line somewhere, how many times does it hit the graph? Well, this vertical line hit the graph just once. Can you find any vertical line that would hit the graph more than once? No, any one vertical line is only going to hit the graph once. So that's essentially saying for each y value, there's a single x value. That's what we had over here. The x values don't repeat. So we say that if the graph passes the vertical line test, meaning mentally put in these lines, and if they only hit the graph in one spot, then it's a function. So this is a function because it passes the vertical line test. Let me just show you this example over here. This is not going to be a function. If you notice, if we draw a line right here, a vertical line, it hits the graph in 2 places. So this one is not a function. It does not pass the vertical line test, okay? What do you think about this graph? Do you think it's a function or not? Well, no matter where you put a vertical line, it's only going to hit the graph once. So yes, this is a function. And then what about this one? Do you think this is a function or not? Well, if you put a vertical line somewhere, you see it hits it in more than one place. So in this case, no, it's not a function. And by the way, I'll just point out one other thing for you, and that is, don't think that it always has to hit twice. Let me show you what I mean. Let's say we have a graph that looks like this, and it stops here, and it stops here. Is this a function? Well, it passes the vertical line test over here, but it fails the vertical line test over here. If there's even one spot where you can put a vertical line and it hits in more than one spot, that's not a function. Because I want you to notice, let's say that this is the x-axis and this is the number 5. You have a 5 associated with this y, and you have a 5 associated with this y, and that's going to mean that the x value 5 is being used twice. I'll just show you. Let's say this is 2, and let's say this is 6. So you have 5, 2, and you also have a 5, 6. So you have the x's repeating themselves. That's no good. This is not a function. Okay, so that's how you tell if a graph is a function or not. All right? Okay, we got more to do, though. We have to determine what the domain is. Now, when we looked at these problems over here, the domain was just all the x values. But how are we supposed to deal with it here? What are all the x values here? Let's see. Well, every place that you can find an x and then go up to the graph, that counts as an x that works. That's a good x. Now, it looks like there's no x's that don't work. Actually, now you might say, what about out here? There's nothing out here, but actually because this line has an arrow on it, it would actually continue out and it will hit an x. So we could actually say the domain is all values for x. And there's a shortcut for writing this. I'll put it on a separate sheet of paper so you can appreciate it a little bit. Okay, all x values, everything, the domain is all x values. You could write it as this shortcut, x, and you make this little, it's a C with a line in it, make a C with a line in it, and you're gonna put an R with another line in it. And what this means is the x values are an element, this funny E is an element of the real numbers. So basically this represents every number you can imagine, right? Every real number. This represents basically everything that's in here is a legitimate value for x. So this is basically saying all x values. It's just a funny notation. So when you want to say all x values, you write XER in these brackets, these braces, and that's going to mean all x values. So the domain for this, because it goes on forever, is XER. The R with that line down it, that means the real numbers. It's just a funny symbol for meaning the real numbers. The range. Well, the range are all the y values that are available. Well, if you take a look horizontally, no matter where you look, the graph is there. And even up here, beyond the graph, the graph doesn't stop here. The arrow indicates it's going to go on forever. So it seems like every y value is going to be in the range. So how do you think we're going to write that? We're going to write y, e, r. With that funny looking r with the line down it. This means all values for y. Every value for y is going to be an element of the range, okay? Every value for y. Okay, let's take a look at our next problem. All right, this is a little hard to see, but I want you to notice it's a parabola, it's this curve, and it goes on forever that way and that way. Now, we already determined it was a function because it passed the vertical line test, and the next thing is to determine the domain. What's the domain of this function? Well, we want to determine what x values work. Well, if I go to an x value like 1, yeah, the graph is there. What about 2? Yeah, the graph is there. 3, yeah, the graph is there. 4, yeah, the graph is there. Now you might say, okay, how about here? Oh, the graph's not there. There's nothing there. But this arrow is pointing out. And ultimately, if you continued it, it will touch. Now you might say, okay, maybe if you continued it there, it will hit, but certainly way out here it won't. Actually, it will. This is going to go slowly, but surely out to the right. So basically, as long as the arrow is a little bit facing in that direction, you know that every value for x on this side is going to be fine. And the same thing is going to be true on this side. So here, what we're going to say is the same thing. The arrows go out this way. Every value for x is going to find the function. So the domain, just like here, is going to be all real numbers. Now, before you write down the range, look at it very carefully. The range is not all real y values. Yeah, sure, if we put horizontal lines, it hits the graph here. It hits the graph here. So like at 1, 2, 3, it hits the graph. Even at -1, it hits the graph. Even at -2, it hits the graph. But it curves around here, and it never goes below here. There's nothing down here. It's all empty down here. So what's the lowest value it goes to? Let me count that. -1, -2, -3. -4 is the lowest value. -5, -6, there is no graph down there. Absolutely nothing. So y's actually start at -4 and then go up forever. You see, it clearly goes up forever, but it doesn't go below this turning point here. So for the y values, we get that y is greater than or equal to -4. It starts down at -4 and it goes up forever. It's greater than -4, but there's nothing below this -4. So the range starts here, starts at -4, and then goes up forever. That's how we write it. Y is greater than or equal to -4. All right, let's take a look at the next problem. We see that this is a parabola too. It's on its side. And let's talk about the range, the domain first. This is not a function because it doesn't pass the vertical line test. The domain. Well, the domain is what x values are available for this graph. Well, there's an x value here at 4. There's an x values here at 2 and at 0 and -1. But over here, there are no x values. So the domain doesn't continue beyond here. So what's the smallest value you get where the domain exists? Right here, which is at -1 to -3. But then it does go up forever. So the domain is x is greater than or equal to -3. It starts at -3 and it goes up this way to the positive numbers and it continues on forever. But on this side, since it turned around, there's no arrow over there. There's nothing over here. It's all empty. It's all blank. So there is no values for x for this graph over here. So the domain is not going to include anything that's less than -3. It's going to start at -3 and move up to infinity. Okay, so x is greater than or equal to -3. Okay, the range. Range is going to be the y's. Are there y's down here? Are there y's up here? You can look at the y-axis and you see that there's some y's over here and there's y's over here. As long as you make a line across and it hits the graph, you know there are y's there. Now you see down here, you come down here and you see, oh, the graph is not down here. But again, there are arrows here. And the arrows point down, very slowly going down, but it's going to go down. And up, it's going to go up very slowly, but it is going to go up. and it will ultimately hit every y down this way, and it will hit every y up this way, and it will go up forever and down forever. So here, it is all values for y that are going to be part of the range, okay? Okay, here's an interesting one. We said that this was not a function because it didn't pass the vertical line test. Let's talk about the domain. Well, there are no arrows on this. It's a circle, clearly no arrows. So it has starting points and ending points. Let's see, are there x values over here? We'll start with the domain, which are x values. There is no circle over here, but the circle starts right over here at -2. At -2, the circle starts, and there are values at -1 and 0 and 1 and 2 and 3 and 4 and 5 and 6. But then past 6, again, it's all blank. There's no circle over here. So the domain starts at -2 and it goes up to 1, 2, 3, 4, 5. I just wanted to check. Yeah, it goes up to 6. So literally, the x values that are good are between -2 and 6. And remember, we learned how to write this notation yesterday. This was in our last lesson. This is a compound inequality where x is everything in between -2 and +6, from -2 to 6, including -2 and +6, because -2 is good and +6 is good, and everything in between is good. So that's going to be our domain. Our range is going to be our y values. And we got to, again, we have no y value. There's no y values up here. No y values down here, but there is a y value down this low, lots of y values here, and there is a y value this high. So let's find those numbers. The lowest y value is -1, 2, 3, 4, 5, 6, and it goes up as high as 2. So our range is going to go from -6 is less than or equal to y is less than or equal to +2. Basically, every value for y, starting with -6, working all the way up to +2 and including +2 is going to be part of the range because the graph is there. But it's all empty up here, so we don't want any values bigger than 2. And there's nothing down here, so we don't want any values lower than -6. So that's how you determine domain and range and determine whether something's a function. If it's a graph, we use the vertical line test. So that's the little preview or introduction to domain, range, and basic graphs. And now we're just going to go and turn our attention now to one other thing. We're going to spend a few minutes just talking about slope. Slope is an important relationship in a line. It relates how the graph is slanted, and it really pertains to straight lines. And the formula for slope, there's two formulas I want you to know. One is the algebraic formula for slope, and that's going to be y2 minus y1 over x2 minus x1. Oh, and by the way, the letter m represents slope. So when you say m, when you see m equals, that's representing slope. So you can compute the slope if you have coordinates, and I'll show you how to do that in a bit. Another way of writing slope is rise over run, and this is a helpful technique if you have a graph, okay? So we're going to take a look at how to determine the slope of a line using both of these formulas, and we're going to practice it more in class tomorrow. And we'll do, we'll practice it and we'll go over it again. So hopefully, even if you don't get it here, you'll get it in class. All right. So let's talk about the graphical way. So the points were -2, 3. I'll rewrite them. -2, 3, and 0, -3. -2, 3 is here, and 0, -3 is here. And this is the line, and I'll put it in red so you can see it. That's the line, and we want to find the slope of it. So what I want you to notice is, if you make this little triangle here, a line straight down from the starting point here, down to flush with this bottom point, and then straight across, if you make this little triangle, then you can count boxes. And the number of boxes on this vertical segment here is 1, 2, 3, 4, 5, 6. 6 units, okay? And the number of boxes along the bottom of this triangle is 1, 2 units. Now, this is called a run, because how do you run? You run horizontally. If I want to run, I have to run across a floor. I can't run on a wall unless I'm a bug, but my run is typically on a floor, right? Now, rise is going up or down, because a negative rise would be a fall. So we're heading down, So that's going to be a rise of -6 because we're going down 1, 2, 3, 4, 5, 6. That's a rise of -6. And our run is 1, 2. So literally, you're going to go along your graph vertically and then horizontally. Since we have to go down, we're going to do a -6, and then we're going to run. We're going to run to the right. Moving to the right is a positive. We run +2. If we're going to do the slope using the graph, we do slope equals rise over run. And rise was -6 over +2. And we get a slope of, this reduces to -3. -3. That means every time we go down 3 units, we have to go to the right 1 unit. Down 3 units, right 1 unit. Down 3 units, right 1 unit. That's what a slope tells us. Typically, it's written as a fraction. If it's a whole number, you don't need the denominator, but it's helpful to have the denominator so you know it's a fraction, which is what a slope is. Now, what about algebraically? If you don't have a graph, or you prefer to do the algebraically, you take the points. I'm going to rewrite them one more time, -2, 3, and 0, -3. And we're going to use this formula. Now, we have to remember the left number is an x, the right number is a y. You have two, I'm sorry, that's wrong, x and y. And we could call this x1, y1, and x2, y2. Now, why are we using those values for x1 and x2? It doesn't really matter. This we'll call point 1, just for convenience. This is the first one, so I called it point 1. And I'll call this point 2, just because it was the second point, okay? So this is x and y, and because it's point 1, I'm calling it x1, y1. This was point 2, and this is x and y, so I called it x2 and y2. And now I'm going to use this formula. I'm going to do my slope is y2. I'm going to just follow this formula. I'm going to substitute this -3 in there. -3 minus, there's a minus in this formula, -3 minus 3 over, now we're going to do x2 minus x1, 0 minus -2. Let's see what that gives us. So slope equals, if you put this in your calculator, -3 minus 3, I'll show you right now. If you go to -3 and then we subtract 3, that gives us a -6. Now I'm going to do 0 minus, parentheses, -2, and that gives us +2. Okay, if we reduce this, oh, that's exactly the same. That's a slope of -3. We got the same answer whichever way we decided to do it, whether we decided to do the graphical way using rise over run, or whether we did it the algebraic way using y2 minus y1 over x2 minus x1. And again, we'll practice this more during class so you'll get good at it, okay?